Good morning, ladies and gentlemen. So welcome back to Mr. Lee Physics class. So today we are going to the new chapter. That's for the chapter for electric. So ladies and gentlemen, we use electricity every day to run or to operate our electronic in our daily life. Let's look at the circuit. So once I switch on the cooker, so we notice that the cooker is working. Once I switch on the air conditioner, the air conditioner will give us the cold air. Once I switch off the power point, the TV will on. And also when I switch on the light will give us the light. So this means that the lamp will light up our rooms. So ladies and gentlemen, this is what we'll learn. All this is because of the electricity. Now we go to the next lesson. Next slide. In this lesson, you were able to understand the electric current as the rate of flow of charge. Understand the mechanism of conduction of electricity in matter. Objective number 3, understand the drift velocity. And objective number 4, derive and use the equation where the current I equal to NEAV and know the typical order of drift velocity, and define the current density for J and derive the equation J equal to conductivity times with the E. Okay, ladies and gentlemen, now we go to the slide lesson. Let's observe the circuit. The circuit with a battery connected to a switch and then series connection to an ammeter and also a bulb. When the switch is connected or the circuit is off, the circuit is connected, the current flow. The current flow through the ammeter and cause the ammeter show some reading. The bulb light up because of the electric current flow. So we look at the current's direction. The current's direction, current flow from the positive terminal to the negative terminal through the external circuit. Okay, so means that here, class, once we mention the external circuit, that means positive to negative through the external circuit. If positive to negative terminal through the internal circuit, that means the direction will be opposite. That means from positive to negative. So from here, the current flow must from positive terminal positive to terminal negative through the external circuit. And the flow of the electron is from the terminal negative to terminal positive through the external circuit. As a conclusion, we can say that the current's direction is always opposite to the electron's direction. In previous lesson, we know that Q is equal to IT. That means that when the charge is flow, okay, when the charge is flow, that means that now we notice that electron is a type of negative charge. Once the negative charge move in the conductor, let's say the conductor with the cross-sectional area of A, the charge flow from right to the left. The current So current I is equal to dq over dt, make sure in ampere, where A or coulomb per second. Current, the unit SI unit is coulomb per second, where the spatial unit is ampere. Next, let's look at the current again in the circuit. If a constant current of 0.5 ampere flow in the circuit, how long will it take for a 10 coulomb charge to pass through the emitter? Means what? We use I equal to dq over dt. And rearrange, we want to find out how long. That means find out the time. That means dt is equal to q over I. So that means 10 over 0.5. We get that. Substitute all the value into the equation. Then we get that 10 over 0.5. So this means that we need 20 seconds to allow the 10 coulomb of charge flow to produce 0.5 ampere. As a conclusion, we can say that the direction of the current is taken should be the direction of the flow of positive charge. This is opposite to the direction of the flow of electron. Current, the direction of current actually is the same direction with the positive charge, where the negative charge is always opposite direction. The flow of the negative charge always negative, always opposite the direction with the positive charge, always opposite direction with the flow of the current. And electric current is the rate of flow of the electric charge, where I current equal to dq over dt. And the unit for current is ampere, spatial unit, which is equivalent to coulomb per second. Coulomb per second is SI unit. Okay. Next. Okay. Now we notice that why a metal can conduct electric. As we learned before, metal is a good conductor. Metal can conduct electric. That means that metal is a good conductor of electric. No matter either metal is a good, as we know that metal is a good conductor of electric, also the conductor of heat energy. When we learn in SEM 1, metal is a good conductor of heat. Why? The same reason with why the metal is a good conductor of electric. Metal can conduct electric well because metal consists of a lot of free electrons that move randomly and freely. So this means that metal with a lot of charge, this means that either positive charge or negative charge, the charge is more easier, more charge, that means that more motion. Once the charge move, means while it will produce the electric. So that is why the current is more easiest to flow through the flow in a metal. Reason? Because of the free electrons that move freely and randomly. Now, the thread of the electron, we notice that the electron is moved randomly and the electron is moved to random direction, or most easier, we set it to all direction. Okay. Okay, next. We go to the next slide. Now we look at here. If the electron flow in the electric field, the free electron flow in the electric field, that means that this will be the direction. We notice that the charge is flow from left to right now. Before that, as we know that if the difference in these two diagrams, this electron, this matter, which the free electron move freely and randomly without any electric field. When the matter is in electric field, means why you see electric field, okay. Once if there is an electric field, that means that we connect to, that means left side or left side and right side are connected to different terminal of the source. That means one side is positive, one side is negative. Okay, can you imagine left side and right side with a flat matter which are charged with positive and negative each. So that means that in between the positive and negative terminal, it will produce an electric field. Negative charge with negative. Okay, electron consists of negative charge. The natural characteristic of negative charge is attracted to the positive charge, attracted to the positive terminal. Okay, that means negative and positive always produce an attractive force. So from here, now we notice that the electrons move from left side to right side. That means that right side will be the positive terminal and left side will be the negative terminal. Negative and negative repel each other. So the electron move away from the negative charge, okay, negative terminal to the positive terminal. What will happen if I increase? You notice the motion, Once I increase the electric field strength, okay, so that means that this is positive, right? Negative. So that means that we notice that the E increase. If I reduce a bit, okay, if there is none of the electric field, that means that if the electric field strength is 0, that means that the electrons move randomly and freely. If the electric field direction is from right to left, okay, if the strength increase, means while the electron will move faster. If in other direction, that means that the electric field in opposite direction, that means that you see or not, it's always electric field is from positive to negative. Positive out, negative in. So positive, that means now we notice that the positive will be this side, negative will be this side. So the electron now move in orderly. Okay, the electrons now not move in randomly. The electron is not moved freely. The electron now is flow. The electron move due to the electric field. The electron now move is under influence of the electric field, and the speed of the electron or the velocity. Why? Because why I said it's velocity, not speed? Because the velocity, because the electron with the direction. So the velocity, we call that is the drift velocity. Now, look at that. The electrons now is moving in the control of the electric field, in the influence of the electric field. So we notice that the electron, okay, track of the electron, no matter how it's moving, it's always moved from left to right. It's still moving left to right. Okay, so although the path may be a little bit curved, but no matter how, it's always left to right. From the left to right, where is electron is always opposite the direction of the electric field. Okay, we notice that no matter how it's moving, at the end it still moves from left to right, opposite the direction of the electric field. Now we notice that, okay, we go to the next slide. Again, the velocity of the electron, when the electrons is in the electric field, we call that is the drift velocity. Now, the electron, let's say one of the electron, this one, you see, the electron is moving from 10 mm the distance. So that means that in a certain time. So the electron's direction is always opposite the direction of the electric field, or the electric field from between two terminals. Now consider when a battery is connected to a switch and series connection to an emitter, then connect to the end of a conductor. Left side is connected, the left end side of the conductor is connected to the positive terminal of the battery. Okay, so now we go to the conductor. We notice that the positive terminal and the negative terminal, and also don't forget the cross-sectional area. We consider this cross-sectional area are uniform. Okay, so this means that if the cross-sectional area are uniform, temperature are constant for both sides. This means that what happened? It obeys the Ohm's law conductor. Okay, so now we look at here what happened if the switch is connected or the switch is off, the circuit is off. Now the electron is moved from the terminal negative to the positive terminal. Okay, this is the direction of the electron. Ladies and gentlemen, we notice that what will happen, the number of free electrons crossing the cross-sectional area from Q to P is given by the formula of NV, where V is the volume between P and Q. And substitute for V. V equal to AV, the voltage. Okay, the small v is the density distance moved per second. This means that, okay, A will be the cross-sectional area. Total number of free electron, where N for electron, how much of electron N? N is moved per second across PQ is given to NAV. Therefore, total charge Q over T equal to NE equal to NAVE. That means that Q over T is I equal to NAVE. This is the formula we use. I will be the current flow in the circuit. N will be the number of the electron. A will be the cross-sectional area. V is the drift velocity of the electron, and E is the charge of an electron, where it's 1.6 times 10 to the power negative 19 coulomb. Okay, ladies and gentlemen, now let's say for the previous experience last year, okay, when student, let's say, okay, when student gather in the field, school field, Padang. Now, let's say we divide the group. We ask the student queue up into two groups, which is boys and girls. Boys, one group, girls, one group. Imagine boys and girls in one group, left side and right side. When everybody queue properly and the queue, okay, the queue in group done, and everybody stand still. My next instruction is, student, now please queue. Make the queue according to class. So this means we have five class. So now I ask student queue according to class. If I give you 10 minutes to make your queue, so you can relax and do it yourself. Okay, so slowly, right? So that means it's more easier. But if I said that I give you 10 seconds to make your queue according to class, what happened? Sure, you must move quickly, right? Once you move quickly, what will happen? Once you move quickly, that means that sure, there will be some people will collect each other. Push and pull will produce. And maybe you want to move to your class, you move to left side, but some move to right side. Correct or not? Okay, so that means that in this situation, same with the electron. Initially, electron is moving, okay, randomly. Once we want it move in orderly according to the electric field direction, under the electric field influence. So some of the electrons starting, they will collide each other. And the speed surely will slower a bit than the random or freely electron. Okay, now, ladies and gentlemen, once the electrons, all of the electrons are move in the same direction. So meanwhile, the electron actually is forced. The electrons, all of the electrons forced to move in one direction by the electric field. So meanwhile, the electrons will move, not how to say that, the electron is not moving that direction naturally, but is forced by the electric field. Okay, so this we must understand about the drift velocity. Okay, now we look at here. Now we are going to learn about the current density. Still the same thing, same circuit. Battery is connected to one end of the conductor, and the other end connect to one positive terminal and one negative terminal. When the switch is on, we notice that the current is flow from positive terminal to the negative terminal through the external circuit. Current density is given by a formula. J is given, okay. The current density is defined as the electric current per cross-sectional area. How much of the current per area? Okay, so that means that I, from the relationship, current is equal to NAVE. Okay, so that means that the current density is equal to NAVE over A. So cancel each other the A, we left. We get that the J, or the current density, is equal to NEV. N is the number of the electron, E is the charge per electron, and the V still is the drift velocity of the electron. Okay, ladies and gentlemen, this drift velocity, what is the maximum speed of the velocity of electron? Maximum velocity is the is the normal speed of the electron. Normal speed of the electron, the maximum speed is the light speed, 3 times 10 to the power at ms negative 1. That means that for any drift velocity, the drift velocity is slower than the natural speed of the electron. That means drift velocity always or almost near to 3 times 10 to the power at ms negative 1. Never more than 3 times 10 to the power at ms negative 1. Okay, now as a conclusion, we notice that if no battery is connected across a metal conductor, the free electrons are moving randomly at very high speed due to their thermal energy. On the whole, there is no net flow of free electron. Thus, the current is 0. Next, when the potential difference is applied across the metal conductor, the free electrons will move with a very small average velocity, known as the drift velocity, towards the positive terminal of the battery. The relationship between the current and the drift velocity, I is equal to NAVE, where N is the number of free electrons per unit volume, A is the cross-sectional area, and the E will be the charge of one electron. Okay? And V will be the drift velocity. The relationship between the current density with J and the drift velocity V is given by J equal to NEV. But I is equal to NAVE. The reason why J equal to NEV, because J equal to I over A. After substitution, I equal to NAVE into J equal to IA. So we get that J equal to NEV only. Now, we go to the next slide. What are the differences? As we know that metal can conduct electric, right? Metal is a good conductor of electric. Metal can conduct electric well compared to the insulator. Plastic or rubber compared to any metal, so the metal is a good conductor of electric. Metal can conduct electric, but the rubber cannot conduct electric. Okay, these two, one is the conductor, one is the insulator.